This video is about moments. And in this video, we are also going to discuss some concepts that relate directly to moments. What are moments? The nth moment of a given random variable x is essentially a number. If the number exists, it equals to the expected value of x to the power n, right? So for a real valued random variable x, if the expected value of x to the power n exists, this value will be the nth moment of x. In the following, we're going to assume that all the following expectation values exist. So this is the nth moment, and we also have the nth central moment of x, which is essentially the nth moment of the new random variable x minus mu. So the nth moment of the real values random variable x minus mu is the nth central moment of x. And we always use mu in our videos. We always use mu to denote the expectation of x. We always use mu to denote expectation, the first moment of given random variable. And here is the nth moment. We also have nth standardized moment, which is the nth moment of this transformed random variable of x. So the nth moment of x minus mu divided by sigma, this is the standardized random variable, will be the nth standardized moment, right? The expectation of x minus mu divided by sigma to the power n is the nth standardized moment of x, which is the nth moment of this standardized random variable, x minus mu divided by sigma. Based on these definitions, we know they are all numbers can be calculated based on expectation, right? So distributions, we know distributions determine expectations, and those moments, since they are numbers calculated based on expectation, we know distributions also determine moments. And for each of these moments, there are essentially some different numbers, or you may regard them as parameters of fixed numbers for given random variables. We can see that the central and standardized moments are essentially linear combinations of moments. Right? For example, the second central moment, which is the expectation of x minus mu to the power 2, that is essentially the variance sigma square, right? This is a linear combination of the second moment and first moment, that is equal to x to the power expected value of x to the power 2 minus mu times the expected value of x. Well, mu here is the number expected value of x. So central and standardized moments are linear combinations of moments. And moments are quite important numbers to describe the shape of distributions, therefore. For example, the first moment is essentially the mean of a given random variable. So how do we derive those moments? Besides the theoretical calculation using expectation, here we're gonna introduce something interesting. Right? Let's see, how do we use random draws or samples, observed samples, to get estimates or approximations for our moments? To introduce this, we're gonna introduce a new concept that relates directly to moments, which is the sample moments. But before we formally define what are sample moments, let's take a look at one example first. We know from our daily experience, if we toss a coin many times and denote 1, if you and get 1 if you have a head, 0 otherwise, we know the sample average will be closer and closer to the successful rate in the end if you toss the coin many times. Right? The average value will essentially is the successful rate of getting a head. So here, if we denote formally to formalize this story, formalize what we have learned from our daily experience, let's denote xi, which equals 1 if the s-torus is a head, otherwise 0 for a tail. We know the sample average, the proportion of heads among n toruses, will be this random variable, which is the sample average. And we call this random variable the first sample moment, which is the summation of xi, the results you observe, divided by n. This apparently will be a random variable. Right? This is a function of the random variable xi's. But from our daily experience, we know this sample average is more likely to take values in a smaller and smaller neighborhood of the successful rate of getting ahead when n grows larger and larger. So from this random variable first sample moment, in the end, we're gonna get some values very close to the theoretical value successful rate p, which is the first moment. From a random variable, from the sample moment, we can find some approximations for the theoretical value moment. Let's take a look at one simulation exercises. So here, we're gonna throw a fair coin for n toruses and calculate the proportion of heads. So for each time we toss a fair coin for n toruses, and we're gonna calculate the proportion of heads. So each time we get a number, which is the proportion of heads. This is one realization of the sample average if we denote xi equals 1 if head otherwise 0, right? So let's calculate the proportion of heads. This is 1 every time if we toss n times, then we have a realization of this random variable. And we are going to repeat this procedure for 2000 times. Therefore, we're gonna draw 2000 realizations of this random variable. And we have 2000 numbers, 2000 proportion of heads among n toruses. And we're gonna draw the histogram, the density plot of these 2000 numbers. Right here is the histogram of this fair coin toss with n equal to 10. And we repeat this for 2000 times. And this is the histogram of these 2000 proportions of heads among 10 toruses. What would happen if we increase n? As n increases, you can see the realized sample average will be closer and closer in a neighborhood around 0.5. Right? They are more and more likely to take values in a smaller and smaller neighborhood around the true value. So this realized sample average, their random realizations are centering towards the first moment. And we can generalize this result to all moments. From the sample values, we could deliver some estimates for the theoretical values. Here we only focus on the IID sequences, and let's formalize what we have observed from the simulation exercise. Let xi be IID random variables, xi with I from 1 to n, and the kth sample moment is essentially a random variable that is the summation of xi to the power k divided by n. And normally we use mk to denote the kth sample moment of xi's. The most well-known case will be the first sample moment, which is the sample mean. the first sample moment. It also has a extra name sample mean, which is always denoted by X bar actually instead of using M1. So this sample mean is so important. This sample mean gets its own notation, Xn bar, which is the summation of xi's divided by n, right? The summation of xi to the power 1, the first sample moment divided by n. Next is, how do we formalize the statement such that sample moments serve as very nice approximations to moments? We know these sample moments, the case sample moments mk, the first sample moment, the sample mean xn bar, they are random variables, right? They can take different values in each observed sample. For example, if you toss a coin for n equals 10 times, perhaps you get 5/10, but if you try repeat this number again, you get another different number, right? Could be 6/10. So those sample means, for example here, they are random variables. Why do I see some random variables are nice approximations to some fixed number moments? You can pause the video at this moment and try to think about this yourself. Well, so why do we see this statement? Let's consider xi's IID sequences with mean, mu, and variance sigma square. So now we consider, let's focus on the sample mean, xn bar, which is the summation of xi's divided by n. So this is the random variable. What are the properties associated with this xn bar random variable? What is the expectation? What is the variance? You can pause the video at this moment and calculate yourself. The calculation is quite straightforward. By the linearity of the expectation, we know the expectation of xn bar is essentially equal to mu, right? Because the expectation of xn bar, that is essentially equal to the expectation of this function of xi's, right? And by the linearity of the expectation, we know we could move 1/n outside, and we can interchange the order of the expectation and summation. So the expectation of the summation is essentially equal to the summation of the expectation of xi's. And we have identical distributed xi's. So all their expectations, given they have identical distribution, their expectations are the same number, which is given by the condition mu. There are n mu's summed together divided by n, so the expectation of this xn bar is essentially equal to mu. And what is the variance? You can pause the video at this moment and try to figure it out yourself. The variance is also quite easy to calculate because of independence. Well, the variance of xn bar is the variance of, again, xn bar is 1/n times the summation of xi's. 1/n is simply a constant. We can move the constant outside the variance bracket, but do not forget the power 2. So when you move a constant outside the variance, always add the power 2. So this is 1/n to the power 2, and times the variance of I equal to 1 to n of xi's. And this is the variance of the summation of independent random variables. When we have this, we can interchange, we will have independence, we can interchange the order of variance and the summation. So the variance of the summation of independent random variables is essentially equal to the summation of each variances of xi. Now they have identical distributions, so their variances are also the same or equal to sigma square. And there are n sigma squares summed together divided by n to the power 2. So the variance is essentially equal to sigma square divided by n. Now this is a very interesting observation. The expectation remains the same, right? It centers around the constant mu, the first sample moment, or the sample, centers around the first moment, the expectation of xi, right? Well, the variance as n grows larger and larger essentially goes to 0. We know the only random variable type with 0 variance is the degenerated random variable constants. Right? Because if we look at the variance, it's essentially the square distance between this random variable and mu on average. Right? This is the expected value of the square distance between xn bar and mu. If this number goes to 0, basically means, well, this random variable will be only taking numbers in a smaller and smaller neighborhood near this expectation, mu, which is indeed true here based on our calculation. This sample mean is a random variable, but as n grows larger and larger, it eventually goes to a constant, mu. Right? This random variable eventually goes to a degenerated random variable. So from the first sample moment, the sample mean, we get the first moment, a fixed number that can be calculated based on expectation. Note that xi to the power k, they are also IID random variables. Right now we could denote yi equals xi to the power k, and the above results, we can apply the above arguments directly if the xi to the power k has first and second moments, basically saying that the yi has, let's say, first and second moments. Therefore, the y here will have mu y and sigma square y. Then the sample mean of yi, which will be the kth sample moment of xi, will also goes to the expectation of yi, which will be the expectation of xi to the power k, the kth moment of xi. So the logic we have shown here can be generalized to the kth moment, right? The kth sample moment. Under additional mild conditions, if xi to the power k has first and second moments following exactly the same logic, the sample mean of xi to the power k, which is the kth sample moment of xi, will also goes to the expectation, the first sample moment of xi to the power k, which is the first moment of xi to the power k, which is the kth moment of xi. And here we have sample mean. Apparently, we also have sample variance, which is defined by this random variable Sn to the power 2, Sn2. So the summation of xi minus xn bar to the power 2 divided by n minus 1. This is again a random variable, all based on the sequence of the IID sequences of xi, right? So xi is from the sequence, xn bar is constructed based on the sequence. And this is a new random variable here. What are the properties of this sample variance random variable? It's not very hard to show that expectation of this sample variance is equal to sigma square. You can pause the video at this moment and try to do the calculation yourself. The sketch of the arguments is that from this formula, note that the summation of xi minus c to the power 2 can be essentially decomposed into two parts. The summation of xi minus xn bar to the power 2 plus n times xn bar minus c to the power 2. If we choose c equals mu, and let's take expectation on both sides. Eventually, you deliver these results. You can show that expectation of xn2 is essentially equal to sigma square. Okay, let's first show why this one holds true. Okay, so here the summation of xi minus c, you could minus a xn bar and plus a xn bar minus c. Right here, minus x bar plus xn bar, we didn't change the value. And now this summation contains three different terms, right? First term is xi minus xn bar to the power 2 plus 2 times xi minus xn bar times a xn minus c, right? Plus xn bar minus c to the power 2. And we're gonna sum up together from I equal 1 to n. Let's take a look of the middle term here, which is the summation of 2 times xi minus xn bar. Here, this term is the same for arbitrary i's, right? So we could move out from the summation. And what is, okay, we can also move the constant 2 outside the summation, right? So the second term will, if we sum up the second term, that is essentially 2 times xn bar minus c times the summation here. And what is this summation? The summation of xi minus the summation of xn bar, that is eventually 0. Because we know xn bar, that is essentially 1 over n times the summation of xi's. And here are n terms together, so will be summation of xi's minus the summation of xi's. Therefore, what's left in this summation of 3 terms will only be the first and the third term, which is the first and the third term here. Okay? So this identity is true. Now let's fix c equals to mu, and let's take expectation on both sides. Okay? And what is the expectation of the summation of xi minus mu to the power 2? Here, by the linearity of expectation, that is essentially the summation of the expectation of xi minus mu to the power 2. This is the variance of xi, right? So it's going to be n times sigma square. Expectation of this term is equal to n to the power sigma square. And the expectation of the second term, that is n minus 1 times the expectation of Sn2. And what is the expectation of the third term? That is essentially the variance of Xn bar, right? The expectation of Xn bar minus mu, if we choose C equal to mu, that is essentially the definition of variance of Xn bar. So the expectation of Xn bar minus mu to the power 2, this is the definition of variance of Xn bar. And we have calculated that value already. And do not miss the n here. So here is n times the variance of Xn bar, that is sigma square. Let's move the sigma square on the other side. So it's going to be n minus 1 times sigma square. Let's cancel n minus 1 on both sides. Eventually, we have the expectation of Sn2 is equal to sigma square. Based on some calculations, you can also show the variance of this sample variance. So this sample variance is also a random variable, right? With the expectation already equal to the variance, sigma square. And the variance of this sample variance of this random variable Sn2, it eventually will go to 0 as well, as n grows larger and larger. So the sample variance is a very nice approximation for the theoretical variance sigma square of the original sequence xi. So from here, we know from some observed from the from random variable that constructed based on the sample, if the sample size grows larger and larger, if the n increases larger and larger, eventually those random variables provide very nice approximations for some theoretical values. This is the end of the video, where we discuss moments and sample moments and some nice properties associated with them. Okay, thank you for watching this video.